And while we're opening to page 11, we'll take our look at the calendar. So last class, we talked about Fibonacci numbers. Remember 1, 1, 2, 3, 5, that long list of numbers, and how those numbers appeared with respect to the bees and also with respect to that rabbit problem. Today, we'll talk about population growth, and then the next class, we talk about fractals. Then we spend a day talking about math and art. 2 days on cryptography. I'm looking forward to that because it's the first time I've ever taught cryptography, so hopefully it'll be a good experience for all of us. And then I have 1 day that's kind of built in case there's a snow day, and if there is, then everything will get pushed back, and if there's not, then we'll find some way to entertain ourselves on that last day of the semester. And then we review for test number 3, and then finally test number 3 is during finals week, but it's not a cumulative final exam, it's just a third test during finals week. That's happening on December 18. Yes? Because final exams don't necessarily happen exactly at the same time as classes do. They try to make it close, but the time intervals don't always match perfectly.
What if we have another class during that time?
There's no classes on this day. Yeah, the last day of classes is December 17. So there's no classes on December 18, only final exams. That's a Tuesday. Yeah, our last class is the previous Thursday. Yeah. Okay.
The ratio chart that we did in class,
Mm-hmm.
are you going to have that already on the test?
So for the ratio chart that we filled in, you're welcome to put it on the cheat sheet. I'm not going to include any of those numbers on the test itself. So here are the kinds of things that I'm expecting you're able to do. Maybe we can just look at the list here from the learning objectives. If we go back maybe on page 10. Here we go. So in the middle of page 10, it's a list of 4 things I'm expecting you're able to do after last class. So interpret the FN notation. Maybe we can just remind ourselves. The first few Fibonacci numbers were 1, 1, 2, 3. What's next? 5. Remember, you add the previous 2. What's the next one? 8. One more? 13. So the rule is pretty straightforward, just add the previous 2 numbers. But then we had this funny FN notation. So the 13 is what number in the list? Is it the 6th? It's the 7th number. So what we do is we say, to tell you it's the 7th number, we write F for the whole name of the Fibonacci list, and then we put a 7 there. So we're not saying that the number is 7, we're just saying the 7th number in the list. And so this is the 6th number in the list, and the 5th number in the list, etc. So I'm expecting that you can handle that notation. You're welcome. And I'm expecting that you can come up with as many of these as I want. So if I said, give me the first 10 Fibonacci numbers, I'd like you to be able to just do that. So you could list them on your cheat sheet if you want to. I'm expecting you to be able to use Fibonacci numbers to compute other ones. Do you guys remember the crazy example I gave you here at the bottom? I said the 39th Fibonacci number is this massive thing, and the 40th is this one. How would you find the 41st? You'd add those 2 together, right? And how would you find the 38th, which is the one before we subtracted these 2? So I'm expecting that you can do that kind of thing. Lucas? There are other sequences that start elsewhere. The Fibonacci list starts 1, 1. That's the name that we give to this particular sequence. It's called the Fibonacci sequence. But there's another sequence of numbers, maybe I can pull it up online real quick, called the Lucas sequence. So you asked a good question. And here is the Lucas sequence. It starts with a 0 and a 1 instead of starting 1 and 1. But then it changes it a little bit. Okay, lots of stuff on the Lucas sequence. Lucas numbers. Let's try those. Here we go. So Fibonacci numbers are these guys. So we've seen those. Lucas numbers. There's the list of Lucas numbers. Starts 2, 1. I'm sorry, not 0, 1. So if we start with the numbers 2 and 1 in that order, you can see, do we understand why is it 18? 7 and 11. So it's the familiar rule, add the previous two numbers, but are these numbers in the list that we just wrote? No, this is not the same list of numbers, but one sequence, one number earlier. It's a completely different list. And so, yeah, if you recognize this idea of add to go forward, well, then we could subtract to go backwards. And so you can look at the negative Lucas numbers, although you can see actually they're alternating, right? -1, +3, -4, +7. So the Fibonacci list starts 1 and 1, and that's what we call the Fibonacci numbers. But there's other sequences with the same pattern, like the one with your name, that starts a little bit different with the same rule, and you get a completely new list of numbers. Good question. Okay. I'd like you to be able to use the golden ratio to estimate the values of Fibonacci numbers. I suppose we didn't do one of those in class, so maybe we can do one real quick. So suppose that suppose that I tell you that the 7th Fibonacci number is 13. Now this happens to be true, but I mean we see it right in front of us and it's easy enough. And I want to know what the 8th Fibonacci number is. Now the fact is, if you happen to know that the previous two numbers are 8 and 13, then what's the answer going to be? 21. 21 is the answer. But let's pretend that we don't happen to have the 8 in front of us. All we have is the 13 to work with, okay? Now it's silly because these numbers are so small you could just figure it out. But if I gave you the 100th one, you wouldn't want to figure them all out, right? So here's the idea, and I think there was stuff like this in the homework because we didn't do it in class. So here's the idea. We know that if you take the 8th number and divide it by the 7th number, this is what we did in that big chart. And we kept getting numbers that were honing in on something. Well, we gave it a fancy name, but it was about 1.618, I think is the next digit. We called it phi. It's that golden ratio. And so if I believe that F8 over F7 is approaching this kind of funny number, then I could multiply both sides by F7. And this guy would just leave the basement because I'm multiplying by F7, and it would come over here. So here's something that we should believe to be true. It's that the 8th number is roughly 1.6 times the 7th number. Does everybody understand the algebra we did? Multiply both sides by F7.
How do we, like, if we're looking for the 100th, but we don't have 99, how do we figure this?
No, you have to have a starting number. So this technique we're using assumes that you know one number and you're trying to get the next one, but you got to know one. And so I could give you the 100th one and ask you to find the 100 first. So let's see if it's true. We know what the answer is supposed to be. 1.618 times, what is F7 according to the givens in this problem? Yeah, F7 is given to us in this problem as 13. So what I'm saying is if we multiply 1.618 by 13, we're going to get pretty close to F8. Now F8 again is exactly how much? We know it's 21 because we happen to have the previous two numbers in the list. But let's just see how close we are with the calculator, assuming that we don't have. So let's see. So we're multiplying 1.618. That might be a good number to throw on the cheat sheet. That is very close to the golden ratio times 13. And if I said that's close to the next number, I'm certain we would all guess 21 is actually the next number. It's always gonna round. Yeah, but the further you are in the list, the closer the answer is going to be to perfect. Can somebody give me, what was the 19th number? Anybody have it still handy in the Fibonacci list? So the 19th number was 4181. Can you guys try the same technique to try to find the 20th number? You already have it in your list, I know that, but don't look in the list for the 20th. But if I just give you the 19th number is 4181, try to use this idea to estimate the 20th number. So what should we do with 4181? Multiply by 1.618, and we should get something very close to, it's not perfect, but if we round that to the nearest integer, 6765. Was that the right answer in the table? 6765. And actually, I did this 1.618. That's kind of sloppy. I could have done a little bit more. So let me pull up the correct answer. 1 plus the square root of 5. Where's my square root button? I guess I don't see one here. So we'll do that. So that's 1 plus the square root of 5 divided by 2. So this is a much better estimate for the golden ratio. If I take this guy and I multiply it by 4181, 6765.0001. That is darn close to the right answer of 6765. Okay? But multiplying by 1.618 is probably going to be good enough for our purposes. Yeah.
So to get the next
That's right. Yeah, I mean, the technical way to get the next number is to add the previous two numbers. That's the right way to do it. But on the test, I'd expect that you could answer a question like this, where I just give you 1, and then you multiply by the 1.618. And then you'll round to the nearest one. Don't always round up, round to the nearest. There should be one number really close to the, yeah. Okay, and then finally, the last thing on our list of stuff to know how to do is to work with sequences similar to the Fibonacci numbers. I know there were some in the homework that were similar to the Fibonacci numbers. So Patty, I'm hoping that answers your question. Yeah. Good, good, good. Okay, so one other thing about the calendar before we jump into today's material. Today is plan number 2. Plan for project number 2 is due. So hopefully, I've already gotten the plan from some of you, but for the rest of you, I'm hoping that you've got a 1-paragraph project plan in the folders. If you don't have it yet, it's okay. You can give it to me next class. But the idea is to not wait until the last minute to think about the projects. So let me talk a little bit about the projects again, actually. So project 2 is due on December the 11th. Now you can see here that on the calendar I gave you guys on the first day of class, I put the word quotes around due. And here's what it means. Project number 2, I will accept without penalty at any point this semester, including the day of the 3rd exam. So you can just wait until whenever you want, hand me your second project on the day of the 3rd exam, which is the last day we will see each other, and I won't have any lateness penalties. So there's no penalties for turning in project number 1 late. However, if you want a chance to do a revision, you need to give this project to me in enough time that I can look at it and give you feedback and hand it back to you, and you have time to revise it and hand it back to me. And the last date on which we can do that is December the 11th. If you hand me your second project on December 11th, I will read it, I will turn it around and give you feedback 2 days later. You'll then have 5 days to do a revision if you're interested, and then you can hand me the revision on the day of the exam, okay? So again, to be clear, I'm not assigning any lateness penalties. You can hand this thing in to me on the day of the 3rd exam, and that's fine. But if you want a chance to do a revision, and a bunch of people took advantage of the revision opportunity here on project 1, you'll need to hand it to me by December 11th. Any questions on any of that? Okay, then let's take a look at page 11. We're starting here in the middle on number 1. Can we go to Laura? Oh, yes, I do, Melissa. Read number 1, please. Okay, can you guys work with your neighbors and fill in the 3 blanks? What's the next number after 12? I heard 18, and I also heard 24. Why do we have 2 different numbers here? Yeah. Okay, so in this case, one group saw 6 going to 12, and they said, oh, I know the pattern. It's doubling. 12 doubles to 24. Another group, who was it that said 18? What was the idea for 18? Yeah, so if we just add 6. And so it's not clear. In fact, both of these answers are perfectly legitimate. Let's fill in the rest. If we're adding 6 every time, what goes after 18? 24, and then 30. If we are doubling every time, 48 and 96. So here's the basic idea. Today we're going to talk about two different ways in which a population could grow. The population could be people in Greenfield, like how many people live in Greenfield on January 1st of each year. The population could be how much money do you have in your savings account as time passes and the money grows. Really any kind of thing where we use the word population. We're going to talk about two different ways in which the population can grow. On the first row, you could say the population grows by adding the same amount every time. And I think Morgan even used the word linear. This is called the linear growth thing. We'll see the definition in just a few minutes. If you keep adding the same number every time, it's linear. If you keep, all right, so maybe instead of saying doubling, let's use a slightly more mathematical way. What operation is it? It's not, it is called an exponential. It's not adding. What did we do when we say doubling? It's multiply by what number? 2. So if you multiply by the same amount every time, it's got a different name. It's called exponential, as Morgan says. So this is what you guys read about, hopefully, over the last few days. So two different growth models. One of them you keep adding the same number. Another one you keep multiplying by the same number. So we're just going to investigate those today. Let's jump down to number 6, and then we'll come back up and fill in some of the vocabulary. Kristen, number 6. Mm-hmm. Okay, so we got some given problems here about this nuclear reactor, and we're going to write down a formula for this thing called P sub n. Now, P sub n is supposed to kind of remind us of the Fibonacci notation that we had before. F1, F2, F3, and then one of the things we did that was real tough last class was try to generalize to something called F sub n, some general number out there somewhere in the list. So here's what we're going to do. We're going to list how much stuff is in the tank for these first few years. P sub 0 represents how much stuff is in the tank initially at time 0 when we start this experiment. So how much stuff is in this tank initially? It's 35 tons. See that? There are 35 tons in the tank already at this moment when we stop the clock. So there's 35 tons right now. And it says that the reactor generates 5 tons a year, 5 tons each year. So how much is in there at P1, which is 1 year down the road? Is 40. Every year gains 5. How much is there at year 2? Is 45. You see the pattern? So it's the same idea as the Fibonacci notation, the way that we wrote it. 35, 40, and 45 represent how much nuclear waste is in the tank, how many tons. The P0, P1, P2 are just the names that we give to say, here's how much stuff is in the tank at time 0, here's how much stuff is in the tank at time 1, and here's how much stuff is in the tank at time 2. There is a difference between the F notation and the P notation. Do you see it? It's one little difference. Yeah, we don't have F0 in the Fibonacci list. We called the first number in the Fibonacci list F1, and the second number F2, and the third number F3, and that seems perfectly reasonable. But for population growth, generally we don't call the very first number in the list 1, we call it 0 to indicate time 0. We're starting the clock, it's all zeros at the beginning, and then you hit the stopwatch and time starts to pass. So it's a little different. Okay, so up here it just basically says P0 is the initial population and P1 is after 1 unit of time. So it says exactly what we've written there. And what we're interested in is writing down a formula for P sub n, some general formula to figure out how much stuff is in the tank at any general moment in time. So here's what we're going to do. We're going to write P sub n equals. Now, if I'm sitting at time n and I want to look 1 year ago, last year, what's the little subscript that I have to put? is n minus 1. The equation is not true at the moment, but do we understand this idea that p sub n minus 1 refers to how much the population was 1 year ago, 1 year before this general n? It's a leap. It's the same leap that we made last class when we said, oh, you add the previous number and you add the number before that. That's what we wrote, and that was tough for some of us. I understand that. But let's see if we can finish this equation. Every year, how much do we add? 5. So to get the population in the current year, n, you take the population 1 year ago, n minus 1, and you do what with it? You add 5. That's the rule. To get the current population, you look 1 year ago, and you add 5. That's what the symbols mean. Yes, because we're doing number 6. Yes, but if it keeps adding the same amount, then the only thing that would change in this problem would be what? Would be the 5. If it were adding 8 tons a year, it would become an 8, but it would be exactly the same. If you just keep adding the same number every year, it's going to look almost exactly like that every time. The formulas are on the next page. Yeah. So if you say Pn equals 5, what you're telling me is that the population is 5 in every year. And we need to say the population this year has a lot to do with the population last year. It's just 5 more. The other thing that we need to write here is a starting amount. You can't just say the population gains 5 every year. I need one more piece of information, and that's how much we start with. How much do we start with in this case? It's 35. So I'm going to circle or box these two guys right here, and I'm going to box this word. Those two equations are what we call the recursive formulas. Recursive formulas. Remember, the word recur means to happen over and over again. And if you're going to use this formula, well, essentially you're going to list all the numbers like we did here in black. We start with 35, that's given, and then the formula says add 5 every time. And so if you wanted to know the population 100 years from now, you're going to do a lot of work because you have to find the first 99 before you can know number 100. So that's the recursive formula. And then we're going to write this in a different way. So I'm going to write a formula, and then we're going to see if we can dissect it. And then there's general formulas on the next page that will give us some clues. P sub n equals 35 plus 5 times n. So here's what I'd like us to do. Can you guys use this formula to find P2? So instead of n, what number are we plugging in? 2. So plug in n equals 2 over there. 35 plus 5 times 2. 35 plus, remember the order of operations. Which one do we have to do first? We have to multiply first. So don't do 35 plus 5. You've got to follow the order of operations. So this is 35 plus 10, which is 45. Is that right? Is P2 equal to 45 according to what we listed out here? Yeah. And in fact, if I wanted to find P100, do I have to find the first 99 numbers in the list? No. Go ahead and find, let's find P60. Use the P60, 60. Go ahead and use that black formula at the top to find P60. We get 335. If you wanted to find P60 using the black list, it'd take a long time, right? Because you'd have to just find every number between 0 and 59, and then finally you'd be able to find 60. So this formula right here is called an explicit formula. because it can tell you explicitly what the population is in year 60 without having to go through the over and over again calculation that we did the first way. So if you had your choice, which one of these formulas would you prefer to work with? The explicit. Unfortunately, not every problem has an explicit formula. The ones that we're going to look at will have explicit formulas, but there are plenty of instances where the recursive is all that you can do. Life is so complicated that we can't get an explicit thing. You just have to come up with some recursive thing. So those are the two kinds of formulas. And one thing you can do with the recursive formula, with the explicit formula, is answer a question like, I think it's listed here, how long will it take for the tank to fill up? Now the capacity of the tank is listed in this problem. What is it? It's 100. It says it's a 100-ton tank. Can't go past 100. So can you guys use the black equation again and try to find out how long until we get to 100 tons of waste in the tank? So we know the general formula is always 35 plus 5n, where n is how many years you've been waiting. How does the 100 come into play? It's the capacity. So how do we make? So can I write an equation and somehow get the 100 in here? Mike? All right, so you're telling me the answer is 13. That sounds great. And so I think even without maybe writing the equation, this is what Mike was solving. We're looking for when the population reaches 100. When does the amount of stuff in this tank get to 100? So it's not n equals 100, but it's when is the whole thing equal to 100. So you replace, you can see up here, we have the 35 plus 5n there, and Pn, that's the population. And we want the population to equal 100. So 100 becomes equal to the whole formula. And then we can solve, and you follow the same process that Mike said, subtract the 35, and then divide by 5. And we get 13 what? So yeah, P13 is the one we're after. 13 is what? Is that tons of waste? That's years, that's time. That's it. So if you wait 13 years, this thing will fill up. We better have some other solution for what to do with the waste before we get to 13 years. Any questions on that one? Okay, so we can go to the next page. I promised you guys some formulas. So first we'll get to number 7 here, and can we go to Stephanie? 7? Do we buy that? What do you get if you subtract 45 minus 40? It's 5. 40 minus 35 is 5. If you just keep subtracting, you always get 5, so that's why we call it the common difference, because we're subtracting. And so here are the formulas. You can try to memorize them. You can put them on a cheat sheet in preparation for the test. But here they are. The recursive one we wrote first. P0 is just the starting amount. And then the formula that we wrote was Pn equals Pn minus 1 plus 5. That was the formula we wrote on the previous page. Well, it's always that formula, except it might not always be 5. So it's always Pn equals Pn minus 1 plus whatever the common difference is. So again, in English, to get the current population, you take last year's population and you add whatever gets added every year. It was 5 in our problem. And then the other formula that we wrote, I think we boxed it in red. I'll remind us it was over here. So Pn equals 35 plus 5 times n. That was the formula. So how did I come up with it? Well, I just kind of followed the formula from here. You take the starting amount. What was the starting amount? It was 35 plus n times, what was the common difference in that problem? 5. So plus n times 5. I wrote the 5 first. So is everybody comfortable? Like this formula will give us, like you could use this formula to get the explicit version. Okay. All right, so the first problem we did today was this pattern thing, 6, 12, and then fill in the rest. Which version looks like the problem that we just did with the nuclear waste? The top one or the bottom one? It's the top one because we kept adding the same amount every time. Okay, we added 5 tons every time. But if you multiply by the same thing every time, it's different. So let's go to Danny for number 9. Okay, so this is what Morgan had said. He used exactly the right words earlier today. Linear means you're adding the same thing every time. Exponential means you're multiplying by the same thing every time. And then Danny just read this thing about the same percentage growth. So if we look at our blue numbers in this list, 6, 12, 24, 48, what percentage did we gain every time? It was 100%. We multiplied by 2, but you gained 100%. If you start with 6 and you gain 100%, that is another 6, you get 12. If you start with 12 and you gain 100%, you're gaining 12. That gives you 24. We see it? So every time we gain the same percentage, we don't gain the same amount, but we gain the same percentage. So let's take a look at this problem here, number 10. Mike?
Suppose you're offered at the end of the month on the first day of the month, second day of the month, fourth day of the month, so on every day.
Everybody understand the second version? Do we have an instinct? So just think for 10 seconds on your own. I'm about to ask you if you'd prefer A or B. Okay, everybody's going to vote for one of these two. Raise your hand if you prefer A. 1, 2, 3, 4, 5, 6, 7, 8. Raise your hand if you prefer B. 1, 2, 3, 4, 5. Okay, so we're just going to try to figure out which one is better. And it's really hard to understand. Well, it's easy to understand 500,000, but it's hard to understand what you're really getting, starting with a penny and then doubling it every day, right? I mean, at the end of a week, we're at like $1.50 on this one. It's pretty far from the 500,000. Okay, all right, so one more for the 500,000. But let's see if we can't figure this out. So we're going to say that I'm going to call P1 the amount of money on the first day and P2 on the second day. So how much money do we get on the first day? It's 1 penny. So I'm going to write that as $0.01, okay? And then P2 is how much? 2 pennies, so $0.02. And we'll write one more of these, and then we'll be tired of writing them. How much on the third day? 4 pennies, right? So every day we get double what we got the previous day. Okay, so there is a formula we can use, but before we get to the formula, let's just be patient and type it in on the calculator. So here's what we're going to do. You take 0.01, that's what you get on the first day. And then what do I do with it to find the next number? Times it by 2. So that's how much I get on the second day. And what do I do with that to find the next day? Times it by 2. And if I just hit enter, it says, oh, times it by 2. I know what you mean. So we get that. That's the third day. So the good thing is, if we just count very carefully how many times we hit enter, we'll get it right. Okay? So that's the third day, and I'm just going to ask you guys to count along with me. So that's the third day. So we go 4, 5, 6, 7, 8. That's hard for me to read. How much is that? Is that right? 100. How much is that? 10 million. 10. That's dollars. I started with $0.01. It's been dollars the whole time. So on the 31st day, you get a check for 10 million. Well, I don't want to scoff at the 700,000, about $11 million. But that's only one check, right? How much did you get the previous day? About 5 million the previous day. So which one are we choosing now, A or B? B. B, 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 B. Yeah, so it turns out that adding them all together is almost exactly the same as hitting the enter key one more time. So the total of all those numbers is roughly 21 million. It's really close to that. So yeah, that one's much better. You shouldn't feel badly. I think that I read this somewhere. The human brain is not built to handle repeatedly multiplying. We cannot fathom what doubling for the long term does. We could double in the short term, but we just can't even really comprehend what it means to double 30 times. That's what I did here. We doubled 30 times. And we're just not wired that way. So let's see if we can't come up with a better way, because that was kind of annoying to just hit the button 30 times. So here's a better way. There's formulas down here. Let's take a look at them. The one that I want to use, well, let's go ahead and use the recursive one first. So here's a recursive formula when we're doing exponential growth. So we got to be really clear. We had two different kinds of things. You add the same amount every time, or you multiply by the same amount every time. For each of those two things, there were two different formulas. So how many formulas are we looking at today? 4 formulas. Either you add the same thing or you multiply the same thing, and each of those has a recursive model and an explicit model. So 4 different formulas. We got to keep them straight. So let's look at this recursive one for the money example. P0 is the start amount. I'm going to change that to P1 just because we decided to start on day 1 and call it 1 instead of 0. So how much is the start amount in this example? This 0.01. It's a little confusing because it's not P0, but I think we can handle that. And then Pn. Well, what's the formula? It says here you take Pn minus 1 and you multiply by something I haven't even defined yet, the common ratio. What did we multiply by over and over again in this money example? We kept multiplying by 2, didn't we? That's what we did, times 2 times 2. So the common ratio for us is 2 because we kept multiplying by 2. And let's see if we buy that formula. Here's what it says in English. If you want to know how much money you're getting today, you look at how much money you were given when? Yesterday, 1 day ago. And what do you do with it? You multiply it by 2. It's exactly what we did, right? So you can translate this to words and it makes sense. To find out how much you have today, and is today, you look at 1 day ago and you multiply by 2. So that's fine, and that's the formula, and essentially that's what we used when we repeatedly hit enter 30 times on the calculator. But you guys were convinced that for linear, the explicit version was easier to work with, and I think it'll be the same thing here. So here's the explicit version. Let's see if we can't use it. So it says Pn equals the start amount. What's the start amount? It was 0.01 times the common ratio. What did we multiply by over and over again? 2. And then we raise it to the n. So let's see if we can understand what's going on with this formula. Suppose that I plug in n equals 2 right there. So this is really 2 squared. How much is 2 squared? It's 4 times 0.01, 0.04, which is one of the numbers in our list. So how come plugging in n equals 2 works? Well, if you plug in n equals 2, it's like doubling twice. If we plug in n equals 3, we're doubling 3 times. What does 2 cubed mean? What does it mean to cube a number? It's to multiply by itself how many times? 3 times. So if I do 2 cubed, I'm really saying 2 times 2 times 2, right? It's like hitting the enter button 3 times. So that formula right there, if we just plug it right into our calculator, should give us, not that one, should give us the right answer. Where's our calculator? Here. Okay, I'm going to type this formula in, 0.01 times parentheses 2 parentheses. Here's the power button on my calculator. How much was n in our month example? It was 31. There's 31 days. I'm going to put 31 right there. That was a whole lot easier than hitting the enter key over and over and over again. Now, if you're on the ball, you'll see that I kind of did some funny business here. Is that the right answer? Is that how much money? Yeah, that was like the 32nd day. I hit it. Remember we'd said 10 million was what you get on the last day, and then Lucas said, but you also get all the other checks, and I just hit enter one more time. So the funny business is happening because we decided to not call P0 the first number in the list. We called it P1. So normally we're going to call it P0. I like the formulas as they're written up here. We just did something that was a little bit different from the formulas. But do we see the power of this formula here in red? Instead of repeatedly hitting the button, just type it in one shot and you get there. Lucas.
So if you want to do it times 30,
That's right. So we really should have done this guy to the 30th power. So if I do the same thing again, but instead of saying, putting 31 there is saying we doubled 31 times, but we didn't. We doubled 30 times, right? You got your first amount of a penny on the first day, and then starting on the second day, you began doubling. So this would say double only 30 times, and it gives us the 10,700,000. That's a great observation. Okay, so don't worry about the funny business. Like I said, I'm happy with the formulas as they're written. Let's see if we can dive into number 12. Who's our reader now? Mike, did you read already?
yeah.
You did. Melissa, can you read 12, please? Okay, you know what? We're skipping that problem. Let's go to number 14. Gina. Gina, can you do 14, please? Yeah, piece of 1. Go ahead. Yes, good. So that's part A, and then part B, it's exactly the same question, but instead of linear, what's the other kind that we're looking at today? It's exponential. So can you guys work in your groups? Maybe like, I mean, these are big problems, so maybe we'll take something like 5 or 6 minutes. So take your time. I'll walk around and answer any questions that I can, but see if you can answer all the parts of both A and B here. All right, so I think all our groups finished with part A, and that was good. I think not everybody's had a chance to do B, but let's look at that one together. First, I want to be really clear. If you're talking about explicit formulas, sorry, if you are talking about recursive formulas, it always looks the same. Recursive formulas are right here. You write the starting amount, which was 16. You write Pn equals Pn minus 1, always plus whatever the magic number is. What do you have to add to get from 16 to 24? 8. So those two things right there are the recursive formulas, all right? We write them, but generally we're not going to use them. They're not as useful as the explicit ones. So let's look at the explicit ones, or I guess there's only actually one. So the one we're about to write is the explicit formula. It is Pn equals always the starting amount, which was how much? 16 plus n times the magic number that you have to add, which is 8. So that right there is the explicit formula. And that's the one that you're going to use if you want to find P12. 16 plus 8 times 12. The n's both became 12s. 16 plus 8 times 12, 16 plus 96, 112. Okay? That's the answer. The population in year 12 is 112. Again, to be clear, we wrote the blue formulas, but there's no point using them to find P12 because the blue formula would just tell you, oh, you want to know P12? Super. You just take P11 and you add 8. That's a problem because we don't know P11. We could use this formula again, but it would just say, oh, you want P11? Great. Take P10 and add 8. So the recursive ones, we're writing them, but they're not very useful to us. Okay? Let's look at the exponential version of things. This italicized word is the only difference between these two problems, but there's a big difference in how we write the formulas. So let's do the same thing we did before. We're going to have the recursive as well as the explicit. And these formulas we don't have as much experience with, so let's take a look at them together. They are right here, number 11 on the previous page. And here on this page are 4 different formulas. We said we were talking about 4 formulas today. Those are 2 of them. The other 2 are at the top. I urge you to write those formulas on your cheat sheet and also make sure you're comfortable with them. You got to know how to use them. It's not just enough to have them in front of you on the test. So exponential, that's what we're after right now. We're doing the recursive. It starts the same way. P0 is the starting amount. So let's write that here. P0 is how much in this problem? Still 16. Let's go back. Still looking at this purple recursive formula here. It says Pn equals Pn minus 1 times the magic number. Times the magic number. It's different. Take a look at the one underlined in blue. Pn equals Pn minus 1 plus the magic number. That's where you add the same thing. But in an exponential version, you multiply by the same thing. So we're going to multiply by the common ratio. So let's write that. So that formula said Pn equals Pn minus 1 times, change colors here, the common ratio. So let's think about that common ratio. First, the word ratio. Is it add, subtract, multiply, or divide? It's divide. That's what the word ratio means. It means divide. Go back to the very first problem we did here. Look at the blue numbers, 6, 12, 24, 48, 96. What did we multiply by every time? It was 2. Yes, multiply by 2 every time. What if it weren't so obvious that it's, oh yeah, sure, we're multiplying by 2. Well, how could you get 2 using the numbers 6 and 12? What can you do with them to make a 2? You can divide them. 12 divided by 6. Yes? And what if you had the numbers 24 and 48? What could you do with them? You divide them. 48 divided by 24, and we get 2. So when we say the common ratio, we're just saying, oh, take any 2 numbers that are right next to each other and divide them. Divide is ratio, common because you always get the same number every time we get 2. So for this example, well, the numbers aren't so nice. All I have is 16 and 24. I need to divide them. What number goes on top? 24. We'd always divided the second number by the previous number. So to find the common ratio, put it up here, we take 24 and divide by 16. And it turns out that number is 1.5. That's the magic number that you multiply by. And if you understand that idea, and I say how much is 16 times 1.5? You should know the answer without a calculator. How much is 16 times 1.5? It's 24. And 24 times 1.5 is the next number. And the next number times 1.5 is the one after that. So 1.5 is the magic multiplier, the common ratio. And it goes right here in our formula. Take Pn minus 1, multiply by 1.5 in this example. And again, translating this to English, it says You want to know the current population, you look at the number one stage ago, 1 year ago, yesterday, and you multiply by 1.5. Just keep multiplying the current number by 1.5. Any questions on how we got the 1.5? Okay, let's see if we can't use the explicit version. Again, you got 4 formulas. Make sure you are choosing the right one. You got to really be comfortable here with the vocabulary, because I'm going to ask you to use each of these 4 formulas on our test, and you need to know which one I'm asking for. If I say explicit, is that enough information to know which of the 4 formulas it is? It's not. I need to give you another word. The 2 options are the ones Morgan gave us way back, linear and exponential. I need to tell you how the thing is growing before I ask you for the kind of formula, because they each have a recursive and explicit version. So here we're using this one in red. It says starting amount times common ratio to the n. Starting amount times common ratio to the n. Let's try it. Explicit formula right here. Pn equals, that's in the formula. Starting amount, still 16, times the common ratio, 1.5, we found that, raised to the always n. N is in the formula. Go back to the previous page. Make sure you see every number in that formula I wrote in the formula on the page. So that formula says Pn equals start amount times common ratio raised to the n. So let's see if we can't now find P12. The first numbers are 16 and 24. The idea here is we keep multiplying by what number? 1.5. So if you use the recursive formula, you're giving yourself more work than you need to do. The recursive formula would say, okay, you want to know the 12th number in the list? Just take the 11th number and multiply by 1.5. The problem is I have no idea what the 11th number is. To get the 11th number, I need the 10th. To get the 10th, I need the 9th. You'd have to go all the way from P0 all the way to P11 to use the recursive formula. But the explicit's much better. So let's use it. P12 equals. So according to this, 16 times 1.5 to the n. 16 times 1.5 to the is 12 in this case, right? Here's the only time that the n makes an appearance is that number. So whatever number is the subscript, it goes right up there. If I want to find P12, 12 goes right up there. Okay. And this is something we can find on the calculator. 16 times 1.5 to the 12. So I'll do it on this guy. 16 times 1.5 raised to the 12th power. And the 12th number in our list is about 2076. Good question. So let's write this number. This was around, what did I say, 2096? Oh, 2076. 2076, thank you. 2076. Yeah, I rounded it up. Okay, so here's a question. How much is P12 in the linear version? It was 112. How much was P12 in the exponential version? 2076. Should they be the same? Should we be concerned that we didn't get the same number? The answer is, yeah, it's different. It's different rules. When we did the purple one, we just kept adding 6. We got completely different numbers from when we doubled, right? And so even with the same starting numbers, we can get completely different things the rest of the way. So we shouldn't be worried. We're not looking to confirm the same answer twice. It's a great thing to look for, but in this case, it's 2 completely different lists, different numbers. Yes? Yeah, so I'm going to expect that you know all 4 formulas, and I'm also going to expect that I can ask you to find like the 12th number in the list using whatever you'd like. And if you're smart about it, you're going to use the explicit one every time. I'm never going to ask you to use the recursive one. All right, so there is this group thing here. There's not enough time to do it, so I'm just going to give you one more problem kind of similar to the one that we just did. So I'd encourage you to try this bacteria thing over the weekend if you wish. Just a reminder, there's no classes on Thursday or Friday of this week because of Thanksgiving. I'm also pretty sure Wednesday evening classes are canceled. So we're not going to see each other until a week from today. I know you are very broken up about it, or maybe that's what you're going to give thanks about. I don't know. But let's do one other example similar to the one that we just did. P0 equals P1 equals. So I'm just making up a new problem. It's not in the packet. So let's just write these numbers down real quick. So let's say that the two numbers are, we're going to start with 15, and the next number is going to be 20. And I'm going to say this is an exponential model. And I want you to find P sub, I don't know, let's find P sub 14. Yes. Yeah, always called the growth model. I mean, but things could be decreasing. It would be but we can just use the word growth even if it's not going up. Yeah. Okay. P15, P0 is 15, P1 is 20, and it's exponential. So is this one where we keep adding the same number or multiplying by the same number? It's multiplying. So one of the things, so that's a tip off here. Exponential is your key that says we are multiplying by the same thing. So one thing we're definitely interested in knowing is that common ratio. Yeah, what is it that we are multiplying by every time? Yeah. Patty, what did you type in to get that? Patty did this. Do we buy it? That's exactly how we're supposed to find the magic number. You take the second number, divide by the first number. That's our common ratio. You can reduce it. You can write it as a decimal if you want. It's 1.3 repeating. Next thing, I didn't specify whether I wanted a recursive or the explicit. All I want is P14. But which one are you going to use? Explicit. The recursive one relies on knowing P13, which relies on knowing P12. So use the explicit one. So there are 4 formulas. There's only one of them that's appropriate for this. Find it. They're all on that one page. You want the explicit version for exponential growth. Okay, so let's fill in our formula. Let's end that conversation in the corner. Thank you. Pn equals, what's the starting amount? 15 times, what's the common ratio? This is 1.33. And then raised to the n, always raised to the n. And then the last part of this problem, what was I asking for? Was the 14th number. Where does the 14 go in our formula? It goes for the n. So let's just get our final answer and then we will call it a day. The 14th number, I'm copying everything except that n, which becomes a 14. Can somebody type this in for us? $590. Wait. Let's double check. Okay, so I got different numbers coming up here. So what do we get? If I do 15 times 1 point, I'm going to be excessive here. It's a lot of 3's. To the 14th power, 841. Is that all right? Yeah. 841. Yeah, use a lot of 3's. Yeah. Okay. I would probably say round to the, on the test it'll say round to the nearest integer or something. All right, so we'll see you guys on Tuesday. Have a great break. Yeah, another way to indicate the 3's is a bar right on top of the 3. Good.